Students, so we're going to be extending on our understanding of random variables. The last lesson you did was really review of what a random variable is. Remember, a random variable has to be have a numeric outcome, and it has probabilities associated with it. So we're going to be moving into a more specific type of random variable today. So it does sort of require that you understand what a random variable is. And I think that we've worked several problems and we've defined them enough to hopefully have a decent understanding of what they are, because we're going to be talking about something called a binomial random variable today. Okay, let's go ahead and get started. Okay, so in your notes, I would like you to title it with Introduction to Binomial Random Variables. You can start a new page for this. Actually, a new page would probably be preferred, because this is going to be, there's a lot of notes that are going to go with this. So please start by writing what is up top here, Introduction to Binomial Random Variables. So we're going to use the example of this random variable counting coin flips. Okay. So obviously, if we just said, hey, let's flip a coin and state the outcome, that would be a heads or tails. That's not a numeric outcome. But as soon as we change the definition, and you can really do this with a lot of like categorical type variables, change them to counts, you then become a random variable. It is now numeric, and we can treat it like a random variable. So let's consider this scenario. So I want you to write this random variable counting coin flips, and let's write this next. So here's what we want to do. So write this down. We want to count the number of heads that occur in 4 flips. Okay? And if we're going to do that, this should make you think of the old reliable tree diagram. We're going to have heads and we're going to have tails. So H and T. So go ahead and write that down. Then we continue this. HT, HT, and I'm going to go ahead and fill that in. So here's for 2 flips, and then we already know that this is going to get pretty extreme. We're going to draw all this out though. So let's go ahead and let's finish this. I'm going to have you also go ahead and draw the rest of these, this tree diagram. There should be a lot of branches in it, a lot of H's and T's. I'm going to go in here. So let's go ahead and do that. All right, so I've got mine complete on here. Pretty intense amount of H's and T's and branches on here, but this is what we would have done in chapter 4 or chapter 5 with the, unit 4 with the probabilities, these tree diagrams. But the same concept comes to mind here. And last chapter, we would have asked the question, what's the probability of getting all 4 heads, or the probability of getting all 4 tails? But we wouldn't really ask the question, what's the probability of getting 2 heads, right? We could answer that, but we didn't really do it because there are a lot of paths that provide just 2 heads, and we'd have to go through and count those. And then here, an even more complicated question is, what's the probability of getting at least 2 heads? So that could be 2 heads, 3 heads, or 4 heads. And there's a lot of possibilities. We have to sit there and count a lot of these. So, but we're really focused on this. We want to talk about this idea of a binomial random variable. Okay? Why is this binomial? Okay? Well, it is binomial because, introduce the idea of binomial. So in our notes, we're gonna write that down, and we're gonna put some bullet points. It is what's called binary. So the word binary means, in computer language, that's 0 or 1. We say yes or no is sort of what that means in computer talk. For those that have done any computing or computer programming, how we're going to be using it is success or failure. Okay? That's sort of how we need to think about that. This binary. So binomial is binary. Okay? if we had, so what would trinomial look like, right? Well, if we had 3 options, this is a trinomial distribution, okay? So hopefully, I mean, that should make sense. Binary, binomial, 2, right? 2 options each time. It's a yes, it's a no, head, no head, success, failure. That's what we're talking about. And when you think about binomials, that's the first thing that needs to come to your head is, okay, I'm looking at this random variable. Is it a yes or no type of situation? Okay, that's what we want to be thinking about. It has 2 options, okay? So to further enhance this idea of what a binomial distribution can look like, we could ask questions like this. Probability of at least 3 heads. And we could find that. We're not going to compute it right now. We're going to just put example question. Probability of at least 3 heads, and we also need to put the number of trials in 4 flips. That's important as well. Going back up to this, trials are fixed in advance. Okay. Now, the next thing that's important is the probabilities need to be consistent every single time. I can't do this first flip and then have the probability shift on me because that kind of messes all of this up. This doesn't work that way. It's not binomial anymore. If I do one outcome and then the next one's probability changed, we have a term for that. That is called trials must be independent. So that if they're not independent, that's going to mess up some of the work that we're going to be trying to do. These trials have to be independent, okay? And then the final thing, which sort of goes hand in hand, the probabilities must always be the same. Okay? Probability, and we'll say P, of success must always be the same. And so this coin flip scenario perfectly models this binomial random variable, this binomial distribution. We have binary option, which is key to this. Next, the trials are fixed in advance. The trials must be independent, and the probability of success must always be the same. So we're going to look at this video that I recorded yesterday in my classroom of a cool toy that I got for Christmas. So let's go ahead and I'm going to pull that up and we're going to look at that. All right, so let's go ahead and look at this. Hey everybody, I'm at the school building and sort of just in my room. There's no students this week, but I wanted to take a second and look at my new toy that I got for Christmas. I asked for this from Santa Claus and he delivered. So let me focus on that. It's called a Galton board. This thing is amazing. If you've ever seen those Newton's cradles that you can hang out on the desk, that's more of like a physics thing where you like pull the ball and it'll go back and forth. This is sort of like the stats version. So there are 3,000 ball bearings in here, 3,000 up in this hopper, okay? And what happens is you take this and you flip and they're going to randomly go into all these slots. Now you'll notice that it does something pretty cool. Hopefully you're already thinking what I'm thinking. Oh, wow, it makes a normal distribution. And then you'll notice that they even put the standard deviation lines on here, right? So that's sort of a throwback to last section. Now, we're not learning about these normal distributions right now, but we are actually learning about binomial distributions. So this right here is actually a binomial distribution if you look at all these pegs up here. So we'll talk about these numbers in a second, but just like I just showed an example in the video of this lesson, this is a binomial setting, okay? Because as they travel, so I've got my finger up here, as they travel down the hopper, zoom in or focus. They hit that first peg there, and they have to make a choice, right? They can either go to the left or they can go to the right, correct? Then they repeat that choice on the next column. They can go left or right. And then they have to continue making those choices, those binary choices, all the way down. And what happens here is the majority of those pegs, the most outcomes are going to be in the center spot right here. So this is a random variable. You'll notice, look at these numbers here. They're all numbered 1 all the way to 28. Those are the possibilities. Those are the random variables. We talk about this idea of random variable. We have numbered each slot here. So it's a random variable because it's a numeric. Now it's a binomial random variable because you have to make binary choices all the way down. So let's look at this again. Let me show you this. Flip that back. All the balls go back in the hopper. Pretty neat. We flip this guy. Pretty freaking cool. When I got this, I could not stop smiling. Another cool fact about this is that there is one copper ball bearing in here. I have not found it yet. Is that it? Wait. Is today the day? Phone can't focus. I think that's it. Yes, I did find it. Now, holy cow, got to take a screenshot of this. Got it. Wow. That's the first day I found it, and it happened live. You guys got to see it. Now, you'll notice where that copper ball bearing is, right? Look at it. It's right here. Now, what deviations? Well, it's between -1. Sort of a throwback lesson here. Well, if we talk about probability, what was the probability it was going to be between this standard deviation right here and the one on the right? Well, that would be 68%. Well, what's the probability that it would land on the next set of deviations between this one here and this one here? Well, that'd be 95%. Remember, we talked about that. And then you have the third deviations on the outside here. That would be 99.7. And we don't have an option to go beyond that. That's okay. All right, one more point I want to make in this video. What happens if I take this, let me back up a little bit, and I tilt it this direction, right? What happens? Well, let's go ahead and flip it. I'm trying to hold my camera and do this. Hopefully you predicted that that would happen. Now, what happened here is that we have a skewed right distribution. It is still binomial. It's binary, right? Because they still have to make the choices on these pegs up here. Do I go left or do I go right? Well, they're more influenced to go to the left. That means their probability is higher to go to the left, right? What happens when I make it flat? Let's go back down. What's the probability on each peg? Well, each peg has a 50-50 chance, 50% to go left. Like a coin. 50% to go right. And so that's the example that I showed you in before. Yeah, the coin flips. Looking at this video here is we have these probabilities left or right, but it's still binomial no matter what. As long as you have two choices, it's binomial, okay? Now, if we were to talk we wrote down some more rules. Trinomial, that would be 3 choices, okay? But we don't do that in here. We focus primarily on binomial, and this one just so happens to make a normal distribution, which is pretty awesome. Okay, so let's talk about this a little bit more. Referring to these rules that we just wrote down right here, binary. In the video, I talked about this, and it's very obvious. That Galton board actually really models what's happening with the coin flips, right? It's gonna go one direction. It's gonna go to the left or to the right. You could call the left a success. You could call the left a failure. You can decide how you want to define it, but it's going to choose a direction. So it's binary, right? It's similar to what has happened here. If we took this, if I take a screenshot of this, let me take a screenshot and let's do some cool computer maneuvering here with this. Edit, paste, and if we take this and we rotate it, it is looking pretty much identical to what happens up top with this, right? It's almost like these pegs make their own tree diagram, right? So it's meeting that requirement of, okay, it's binary. It looks exactly like it, right? So then set number of trials are fixed in advance. So there are 12 rows of pegs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 12 rows of pegs that these balls, it's 12 set trials, right? So it's meeting that requirement of, oh, there are a set fixed number of trials, right? Are the trials independent? Does the first peg getting hit, so let's say that I'm one of these ball bearings. I hit this first peg and I go left. Does that first outcome influence second outcome? No, it still has the choice to go right or left, and it's still 50-50, right? It's keeping that same probability the whole time, just the way that this is constructed. And it's going to continue to do that all the way down. They are independent. The first outcome does not change the second. And so that's that idea of independence. And we just also verified that the probability of success must always be the same. And that's what's happening. Now, in the video, when I took this board and I tilted it and then flipped it, we start to see the pegs. It happens so fast. They're starting to stack up on this left side. And what happens is the probability to go to the left is higher than it is to the right. Now, it's still binary, but it's almost like me taking this and tilting it this way and saying, okay, it's no longer 0.5 and hold on, let me write this. It's no longer 0.5 and 0.5. What we end up with is something that is more on the lines of maybe 0.8 and 0.2, right? And we expect more outcomes, and if that continues, we expect more to happen down here if we're writing out our probabilities and creating this distribution. We're expecting more tails to actually happen on here. Counting the number of heads, we're going to get less and less heads. So the probability of no heads becomes higher, okay? The probability of all heads is much, much lower, and it becomes skewed to the right like we see here in this video. You guys can hopefully understand why I was so excited about getting this. It's perfect to teach this lesson with here, okay? And it relates very closely to the coins. As soon as I took this back to a level state, as soon as I made it 50-50 again, we end up with a beautiful normal distribution for the random variable, like we would see if this probability here was 50-50. Now, if the probability of success and failure is 50-50, you do expect to get a normal distribution from these binomial random variables. Okay? It's 50-50 all the way down. But not all of our random variables are going to look like that. Okay? But this is sort of our introduction into random variables. So let's talk a little bit about a random variable. Let me start a new page here. We're going to write down some definitions. So let's go ahead and write this in our notes. A binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. Okay? Now, how we identified it, we already wrote out these rules on the last slide. Okay? But we're going to use what's called bins. Okay? This is something you need to keep in mind when you're trying to identify if it's a binomial setting, okay? So the first thing, B stands for binary, success or failure, okay? That's sort of the simplest way to put it. There needs to be two options that happen each time you're going from trial to trial, okay? Next, independent. Hopefully we know what that means by now. We've talked about independence so much, and I told you early on that it was going to be important. This means one probability does not affect the next. If it does, then we can't do calculations, which we're going to get to soon. But today we're just introducing the idea. Next, in set number of trials. So is there a set number of trials already laid out? Okay. Last, probability of success is the same for each trial. Kind of already wrote that, but I wanted to rewrite it again because this is what you have to use to answer a lot of questions. Okay. So, let's go ahead and we're going to practice. Yeah, this is what we're going to do. We're going to have some practice problems that we're going to be working on. So let's look at these questions here. So on this one, it says you're going to shuffle a deck of cards, turn over the top card, and put the card back in the deck and shuffle again. Repeat this process 10 times. So our random variable is x equals the number of aces you observe. Okay. I'm going to work this one with you, and then I'm going to have you try number 2 and 3 on your own. So this is what you should do each time you're trying to decide, is it a binomial random variable? Okay. So this will be what you want to do. I'm actually going to put this on a new page here. What? One second. Okay, so I've got those copied in now. And how you should try to start each one of these is writing BINS down on the right side of each question. So for number 1, you can put number 1 out. You don't have to copy the question, but we're just trying to experience this. Write 1 BINS. Okay, and each time you're going through this, because we're trying to determine if the random variable has a binomial distribution or not. Okay, I'm going to duplicate this 3 times. So we're gonna go through here, and I'll be using check marks if it's binomial or not. So first off, number 1, shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this process 10 times. Let x equal the number of aces you observe. Okay, is it binary? So can we define it? Is it defined as success and failure? It says number of aces. Well, you're going to draw a card. You will get an ace or you will not get an ace, right? So that is binary, right? It's a success or failure. That's how that works, okay? Next, independent. We take the card, we put it back in. This is with replacement, right? We talked about that last chapter. Anytime you have the with replacement happening with cards or anything, it is automatically independent because the probability of getting an ace on the next draw should be the same. So because you're randomizing, you put it back in, you randomize, and then your probability should be the same as the first time. Next, is there a set number of trials in advance? Yeah, it says do it 10 times. 10 trials. Yes, so check mark. Last, is the probability the same every time? Again, that's sort of a repeat of the independent. Check mark. There we go. Okay. All right, that's how you do that. Now, I'm going to pause it. I want you to try to do number 2 and number 3, and then we'll go through them. Okay, so let's talk through this. You have your answer. It says choose students at random from your class. Let y equal the number who are over 6 feet tall. Okay, so first off, binary. Is it binary? Well, you're going to pick somebody, and they're either going to be over 6 foot or they're not going to be over 6 foot. Okay, next, is it independent? You're choosing a student at random from the class. Are you putting them back? That's my question. Are they getting replaced? Okay, so looking at the textbook, it says, because we are selecting without replacement from a small number of students, the observations are not independent. So right away from there, we don't have to continue this because automatically it fails to be a binomial distribution. It's not a binomial random variable. It's still a random variable, but it's not a binomial random variable. Is there a set number of trials? For some reason, the book says that there's 3, but nowhere in here does it actually say that there's a set number of trials. So for me, that's an X. Is the probability the same? Well, no. If the class only has one person that's 6 foot tall and I pick them first and I don't put them back, automatically the probability becomes 0. So the probability is not always going to be the same without replacement. However, the book is saying the probability of success will not change from trial to trial. I don't think they got that one right. Might need to write the book editor on that one. Okay, next, number 3. This is an interesting one. Roll a fair die 100 times. Sometime during the 100 rolls, one corner of the die chips off. Let W equal the number of 5s you roll. Okay, so we're interested in 5. So is it binary? Well, if you get a 5, it's a success. If you don't get a 5, it's a failure. So again, we have that idea. It's binary for sure. 5 is success. Don't roll a 5 is failure. Independent. Are die rolls independent? Oh yeah, we've talked about that. We have listed out things that are independent. Die rolls are definitely independent. So are coin flips. Okay. Next, is there a set number of trials? Yeah, 100. Okay. Now, is the probability going to be the same every single time? Every single trial? Okay. So this is a situation where we see that even though these are independent events, have a probability changing because one corner chips off, the weight of that die is now changed, right? The probability at the first trial is now different. Every trial has to be the same. So this last one here doesn't work, okay? That one fails. So the only one of these that is a binomial distribution is number 1, okay? We're going to do one more example from our problem set. Everybody should have their problem set. Remember that those are due this semester. Where is it? Here it is. Okay, let's look at this. Let's look at number 29. Let's copy that in here. And I'm going to go back and I want to get my bins. Copy, paste. And we're going to have to do this for each one of them. Okay? So for number 20, it says, for which of the following counts would a binomial probability model be reasonable? Okay. The number of traffic tickets written by each police officer in a large city during 1 month. The number of traffic tickets written by each police officer in a large city during 1 month. Well, it's definitely numeric. But let's think about this. So looking at this one, I believe, first off, the big issue here is that there are no set number of trials in advance. You're counting number of traffic tickets, but there's nothing like a set number that's happening here. Also, the probability of success, officers are stationed different places. So there's no way that we have same probabilities. They would be independent, and then you give a ticket or you don't. So it kind of is binary, but because of these last two, I'm going to say no on that. Okay. So for me, it is not A. And this is the thought process you want to have when you're looking at some of these. Next, the number of hearts in a hand of 5 cards dealt from a standard deck of 52 cards that has been thoroughly shuffled. So I take issue with this one being binary, okay? Because you could get 0 hearts, 1 heart, 2 heart. You could get a full hand of hearts, right? But they haven't defined what success is here, right? They should have said getting 4 hearts in your hand in a hand of 5 cards. There's not really a success here. Now, it was thoroughly shuffled, but also you'd put them back, draw another set of cards. We don't really have a set number of trials either. Okay? you're drawing 5 cards, so that kind of sounds like, okay, 1, 2, 3, 4, 5. But if you're doing it that way, then it's no longer independent, right? The probability of getting a heart changes as you draw. So there's a lot of issues with B as far as independence and how it's being defined. Next, the number of 7s in a randomly selected set of 5 random digits from a table of random digits. So first off, it's binary because you have success or failure, right? You get a 7 or you don't. You're going to have, these are random digits. One digit does not affect the next, so they're independent. Set number of trials, you're going to take 5 random digits from a table of random digits. There we go. And then probability should be the same. It's 1 out of 10, right? Because it goes from 0 to 9. This one is good so far. And we know that it's not all of the above. Number of phone calls received in a 1 hour period. Yeah, that sort of doesn't have a set number of trials on that one. So this one doesn't work. So C should be the best choice. This is a difficult problem for sure. But that's the kind of thinking that you want to have. Okay, is it binomial or is it not? And so we're going to stop the lesson here with this example. There's a couple other examples that you can do on here. We don't really know what a geometric distribution is yet, so we can't really talk about that. Is there nothing you can do? Maybe on the last one. Let's see. No, so not until the next lesson will you be able to do some of these other ones. Okay, so we'll go ahead and stop there.